Section 6.4 is the central limit theorem. In the previous section, we saw that the sampling distribution of the sample means tends to be normally distributed as the sample size increases. So next page says, given any population in any distribution, uniform, skewed, etc., the distribution of a sampling means can be approximated by a normal distribution when samples are large enough. And for us, large enough means that it has to be greater than 30. And so it says the central limit theorem says regardless of the shape of the underlying population, the sampling distribution of x bar becomes approximately normal as the sample size n increases. So if n is greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with mean mu and a standard deviation equal to, and our standard deviation is going to be sigma divided by the square root of n. The more skewed the distribution of the population, the larger the sample size needs to be to invoke the central limit theorem. So the central limit theorem and sampling distributions of x bar, and the image that's right up above shows it's very skewed to the right, and you can see that traced line on there. That is a normal curve, and the histogram is very skewed to the right. But as our sample size increases, you'll see that the histogram is becoming more and more normal. So it's approximating the normal distribution. So right below that, it says the central limit theorem and the sampling distribution of x bar. Suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. If the population has a normal distribution, or n is greater than 30, then the sampling distribution x bar has a mean and a standard deviation given. So again, the mean is just equal to itself, the mu. Whereas our standard deviation, the little formula that we need to know here is going to be that it's sigma divided by the square root of n, and remember n is your sample size. So right below this, it says if the original population is not normally distributed and n is less than or equal to 30, then the distribution of x bar cannot be approximated by a normal distribution, and the methods discussed above cannot be used. So the distribution of x bar on our MyOpen Math homework is that we were going to have x bar, and again it approximates n, which is our normal distribution, and then on MyOpen Math there's going to be 2 spaces there for you to plug in the information that you have. And again, this is only for x bar, not for x. So in the first box you're going to put the mean, which is just mu. And the second one, you're going to have to calculate sigma divided by the square root of n. The example right below says, based on tests of the Chevrolet Cobalt, engineers have found that the miles per gallon on highway driving is normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. Round your answers 4 decimal places. First off, we know that our mean is 32 and our standard deviation is 3.5, and both of those are in miles per gallon. And so the first one, part A, says what is the probability that a randomly selected cobalt gets more than 35 miles per gallon? So going ahead and drawing our normal curve, because it says it's approximated by the normal distribution. I'm going to go ahead and put my mean in the middle, and our mean here is 32. And this is asking for finding the probability that x is greater than 34 miles to gallon. So 34 is larger than 32, and since it's asking for more than 34, I'm going to go ahead and shade this to the right. So in order to find this probability, we do use normal CDF as we've done before. Where the shading starts is at 34, comma, 1E99, again as our infinity since this does go off to the right. Our mean is 32 and our standard deviation is given as 3.5. On the graphing calculator, we need to go to second vars and then normal CDF, and then our lower bound is 34, comma, upper is 1E, and again that's second, comma, 99. Then comma, we have 32 as our mean and our standard deviation is 3.5. Close your parentheses, select enter, and then round your probability 4 decimal places. From the graphing calculator, we get 0.2839. Part B says 10 cobalts are randomly selected and the miles per gallon for each car is recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? So the difference between this one and Part A is going to be that in Part A it just says a randomly selected, and that word A means just one, whereas Part B has 10 cobalts. And we're still asking about exceeding 34 miles per gallon, and we're asking still about the probability. So this time we're asking about the probability, but we'll also have mean miles. So instead of x, we have x bar, and this is going to be greater than 34. So we're still going to calculate this using normal CDF. But because I have 10 cobalts, this is going to change my standard deviation to being sigma divided by the square root of n. So our shading's still going to start at 34. It's just the same graph as the one that we have up above. Our upper bound is 1e99. Our mean is still 32, but our standard deviation is what changes. So it's 3.5 divided by the square root of n. And n in this problem is 10, since that's our number of cobalts that we have. And I'm going to go ahead and substitute this all in on my calculator, and I'm not going to round that standard deviation. I'm going to type it in as 3.5 divided by the square root of 10. On the graphing calculator, we're going to go to second vars, and then we're going to go to normal CDF. 34 is our lower bound, comma, 1e, which is second, comma, 99 is our upper, comma, 32 for our mean, comma, and then we have 3.5 divided by the square root, and again the square root is second x squared, and then we're going to type in 10 as that was our n value for this problem. And then I'm going to scroll right so it leaves the square root, and then I'm going to close with my parenthesis, so the parenthesis is outside of that square root, not inside of it, and then select enter, and then round our probability answer correct 4 decimal places. From the graphing calculator, we get a probability of 0.0354. Part C says 20 cobalts are randomly selected and the miles per gallon for each car recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? And then would this result to be significantly high? So again, we're still asking about exceeding 34 miles to gallon, and we're still asking about the probability. And so this is exactly similar to like what we had up above with Part B, but instead, because we're asking about the mean miles, this time we have 20 cobalts. So we're still using normal CDF. Exceeding 34, so 34 is our lower limit, 1e99 is still our upper limit. Mean is still 32, but this time our standard deviation is going to be 3.5 divided by the square root of n, and in this problem, n is equal to 20. On the graphing calculator, we are going to go second vars, normal CDF, 34 lower bound, comma, 1e99, comma, our mean, which is 32, comma, and then our standard deviation, which is going to be 3.5 divided by a square root, which again is second square root, which is second x squared. And then from here, I need to type in our n value, which is 20. And then I'm going to use that right arrow to get out of the square root and outside, close my parentheses, and select enter. From here, round your answer correct 4 decimal places. From the graphing calculator, we get 0.0053. And there is a second question in here that says, would this result be significantly high? And the answer is yes. And the reason why it's significantly high is because, so since the probability is equal to 0.0053, which is less than that cutoff, which was 0.05. The example right below says assume that cans of Coke are filled with actual amounts that have a mean of 12 ounces and a standard deviation of 0.11 ounces. Assume that weights of cans of Cokes are normally distributed. Round your answers 4 decimal places. So let's look at part A and part B together. So part A says find the probability of a single can of Coke having at most 12.19 ounces. Whereas part B says each of the 36 cans of Coke in a data set have a mean weight recorded. It says find the probability that the 36 randomly selected cans of Coke have a mean of at most 12.19 ounces. So the difference is that this one is still asking for probability, but about 36 cans of Coke. It wants to see if the mean has at most 12.19 ounces. So the first one is asking about having at most 12.19 is going to be less than or equal to 12.19. And our second one, part B, is going to be X bar is at most 12.19 ounces. So I'm going to go ahead and sketch our normal curve, which we know that the mean is 12, and 12.19 is a little bit larger. And since it says at most, that means it's going to be anything smaller than this. So to calculate that probability, we use normal CDF. Our lower bound, which is negative infinity, will be negative 1e99, comma upper bound is 12.19, comma the mean, which is 12, and then comma our standard deviation, which is 0.11. On the graphing calculator, we're going to go second vars, normal CDF. Our lower bound this time is negative 1e99. Negative is the one that's underneath the 3. So negative 1e, remember second, comma, and then 99. Then comma, our upper bound is 12.19, comma, our mean is 12, comma, and our standard deviation is 0.11. Close your parentheses, select enter. From the graphing calculator, we get 0.9579. For part B, we're going to use normal CDF. Our lower bound is still negative 1e99. Upper bound is still 12.19. The mean is still 12. However, since we're dealing with 36 cans of Coke and n is 36, we're going to now have our standard deviation divided by the square root of n. So we have 0.11 divided by the square root of n, which is 36. On the graphing calculator, we're going to go to second vars, and we're going to go to normal CDF. Our lower bound again is negative 1e99, comma. Our upper bound is 12.19, comma. The mean is 12, comma, and then for our standard deviation, we're going to type 0.11, which is our standard deviation, divided by, and then we need the square root, which is second x squared, and our n, the sample size, is 36. And then I'm going to use the right arrow again so I get out of that square root, close my parentheses, and select enter. From the graphing calculator, we get an answer of 1. The next section that we have is 6.5, which is assessing normality. It says in this section, we present the criteria for determining whether the requirements of a normal distribution is satisfied. The criteria involves visual inspection of a histogram to see if it's roughly bell-shaped, identifying any outliers, and creating a normal quantile plot, which is also abbreviated as NQP. So a normal quantile plot is a graph of points x and y where each x value is from the original set of sample data and each y value corresponds to a z-score that is expected from the standard normal distribution. Procedure for determining whether it is reasonable to assume the sample data are from a population having a normal distribution. Again, these are the 3 things that you need to check. So you have to check all 3. And this section will come up in the projects. So definitely something that you need to go back and look at and review. But it is reminded to you guys as you are working on the project. So the first thing is your histogram. Your histogram is going to be approximately bell-shaped or normally distributed. Outliers, you can either have 0 or 1 outlier, but no more. And then your normal quantile plot, it's typed out for you already, but it says the population distribution is normal if the pattern of the points is reasonably close to a straight line. So we're looking for the pattern of the points being reasonably close to a straight line. And the points do not show any systematic pattern that is not a straight line pattern. Not a normal distribution. The population is not normal if any of the following conditions hold true. So this is if it's not normal. So the points do not lie reasonably close to a straight line on our normal quantile plot, or the points are showing some kind of pattern that's not a straight line on the normal quantile plot. The histogram might not be roughly bell-shaped, and that we have more than one outlier. So for us, a normal quantile plot is never going to be something that you're going to actually have to calculate by hand. It's going to be something that's given to you, or we will use Statis to calculate it for our project. The example right below says a random sample of 100 adult males' blood pressure was recorded. The data was then used to create a histogram and a normal quantile plot, and those are both given to you here. It was also determined that the data has no outliers. Determine whether the data appears to be from a population with a normal distribution. Clearly explain why or why not. So there's 3 things that we have to check in order to say that something is approximately normal or not approximately normal. The first one is that your histogram needs to be roughly bell-shaped. Not exactly, but this one does look like it's roughly bell-shaped. Then you can see that as it's approximating that normal curve that's drawn on there also. So I'm going to say histogram is roughly bell-shaped. Second thing is going to be that we're allowed 0 or 1 outliers, and for this one we have no outliers. It's told to us in the problem. And then the third thing is going to be our normal quantile plot is approximately a straight line and no pattern is given. And you can see that line is drawn on there also, and you can see all those points that are a normal quantile plot, and they're reasonably close to a straight line. So I'm going to say NQP is approximately a straight line. And again, remember that NQP does stand for normal quantile plot. So this is going to be the end of our notes for chapter 6. Make sure to upload them all as a single PDF file.